familiar with it, you know what it is, you can probably recite at least the first couple of digits, 3.1415926, etc. It goes on forever, it's irrational. What is it? Okay, in AP Physics, we're going to talk quite a bit about rotational dynamics and rotational mechanics, and we're going to use radians. So what is a radian?
If you start to walk along a circle, the distance you've walked along the arc is called the arc length. An arc length of 1 radius corresponds to an angle of 1 radian. An arc length of 2 radii corresponds to 2 radians, and so forth.
So that makes pi the number of radians in 180 degrees, or the number of radii in 180 degrees, or the number of diameters in an entire circle. And this number is natural. It occurs regardless of the size of the circle. And yes, that's in base 10, but any intelligent civilization should be able to figure out pi and agree on the number. It's one of the reasons why trying to contact alien life or discover alien life, we're looking around for the number pi being beamed out in some sort of alienish Morse code. Haven't found it yet, but it could be out there. And if we do, it's probably something smart enough to have figured out some interesting geometry. So radians as a unit are natural. It is unitless. We usually write something like 1 radian or 0.7 radians or things like that, but that's really just filler. A radian is a ratio, so it has no units. That means if you take meters per second and multiply by radians, you actually get meters per second. And that's an important point for when we do some math with this later. 360 degrees in a circle is an arbitrary number that somebody came up with many centuries ago, and we've just used ever since. We are not going to agree with another culture or agree with another alien civilization or something like that a circle has 360 degrees. That's just completely invented, and it's probably related to approximately 1 degree per day as the Earth goes around the sun. I'm not sure about that, but that's a good guess. Regardless, everyone will agree on what a radian is, and that around a circle you have 2 pi radians. We can take this relationship between radians and radius and ask some interesting questions, like we can convert, for example, a car's linear speed to the tire's RPM based on the size of the tire. So that is a relatively easy problem to do if you know the relationship between a radian and a radius and a circumference. So let's do it.
It should make sense that a car with a certain linear velocity has tires that have a certain angular velocity, which we represent with a lowercase omega. If omega is the number of radians per second, and each radian corresponds to 1 radius worth of distance, then the velocity of the car must be r times omega. So a car going a highway speed of 30 meters per second would have tires going with what RPM? This becomes very easy. Assuming a radius of 0.25 meters, all we have to do is solve for omega and plug in to get 120 radians per second. From there we just convert radians to revolutions and seconds to minutes, and we get 1146 RPM.
That relationship is broader than this too. So if you have the angular distance in radians, multiply radius, you get linear distance. If you have the angular speed in radians per second, multiply radius, and you'll get linear speed. Same thing with angular acceleration. If you know your angular acceleration, you can get your linear acceleration. Please note that angular acceleration is not the same thing as centripetal acceleration. When your car tire is speeding up how quickly it's rolling, that is angular acceleration. When your car tire is traveling at a constant speed, you still have centripetal acceleration, right? Holding the tire in place to make it go in a circle. All right, those are 2 different ideas. It is entirely possible for something to have both angular acceleration and centripetal acceleration. Those are 2 different things, and the net acceleration would be the vector sum added tip to tail of the 2 of those quantities. The direction of these angular vectors are a little strange. Angular velocity and things, the behavior of vectors I've mentioned before are very different than the behaviors of scalars, and especially when you multiply them. And in order to keep track of that, one of the things we invented is called the right-hand rule. If you have a wheel that's rolling this way, what direction is its angular velocity? Well, it turns out that if you curl your fingers in the direction it's going, your thumb points in the direction of the angular velocity. And that sounds pretty weird. A tire going this way has an angular velocity that way. If the tire is going this way, the angular velocity is that way. Now, so if this thing is going this way and speeding up, its angular velocity and angular acceleration are that way. But if it's going this way and it's slowing down, then its angular velocity is that way. Its angular acceleration is the opposite way, that way. That's how the right-hand rule works. And that's going to come up a reasonable amount. So you just need to know it. Make sure you know which hand is your right hand.
By now, you know these equations quite well. You've been using them for months. Your kinematics equations can be directly translated into rotational kinematics equations as well. If you know that instead of distance, you're going to use angular distance, that is angle in radians, instead of velocity, you're going to use angular velocity, and instead of acceleration, you're going to use angular acceleration, you get some equations that look like this. Now, your average student's first reaction to seeing these is, whoa, that's a lot of Greek letters. They look confusing because of that, but let's take them one at a time. Angular speed equals angular distance divided by time. That one's pretty easy. How about angular speed equals initial angular speed plus angular acceleration times time? The next one, the distance formula, is exactly what you think it is. The angle you're at is equal to the angle you were at plus your angular velocity times time plus 1/2 times your angular acceleration times time. And combining the last two will give us the equation without time, just like we get in the kinematics equations. Because these are the kinematics equations, just for angular quantities rather than linear quantities. Let's do an example. Here's a piece of old technology we used to watch movies on. A DVD starts at rest and then spins up to an angular speed of 32 radians per second in a time of 0.9 seconds. We want to know, what's the average angular acceleration of the disk? How many total radians does it rotate through as it gets up to speed? How many complete rotations is this? If the radius of the disk is 4.5 centimeters, what's the tangential speed on the rim of the disk? And what is the tangential acceleration of a point on the edge of the disk while it's spinning up to speed? And the thing about this question is that the first part can be directly translated into a linear motion problem that you already know how to solve. If I said an object at rest speeds up to 32 meters per second in a time of 0.9 seconds, and then asked you what was its average acceleration and how far did it go, you should be able to do that. So let's start there and then translate it into angular quantities. For question A, if you have change in speed in time, then acceleration is delta v over t. Well, angular acceleration then is delta omega over t. Plug in our numbers and we'll get 35.56 radians per second squared. For part B1, we want an angular distance, so start with the distance formula, x equals 1/2 at squared. That's theta equals 1/2 alpha t squared in angular units. Plug in our numbers, we get 14.4 radians. Part B2 is just a unit conversion, so use the factor label method to convert from radians to revolutions. For part C and D, we have to convert from angular quantities to linear quantities, and that's as simple as just multiplying by radius. V equals r omega, and A equals r alpha. Done.